Have you ever looked at like a highly optimized, super short piece of work?
Oh, yeah.
Like maybe it's a single line of computer code or a densely packed legal contract.
Or even, one of those ridiculously technical baking recipes.
Exactly. And you just look at it and think, this is absolutely brilliant, but I have completely lost the ability to understand what it actually does.
Right. It's that feeling of looking at alien technology. I mean, you can tell it's advanced, you can tell it's super efficient, but the interface is just completely impenetrable.
Yeah, totally impenetrable. And that's actually exactly what we are jumping right into today. Welcome to the deep dive.
Glad to be here.
So, our mission for you today is exploring this constant, fundamental tug of war that happens, well, behind the screens of almost every app and website you use.
Mhm.
We're looking at the tension between what programmers call functional elegance and explicit logic.
Hmm.
And our source material today is a set of technical notes on a programming language called Haskell.
Right. Haskell, which is kind of infamous for this.
Oh, big time. But this specific technical friction highlights a much bigger universal dilemma for you, the listener, no matter what field you're in,
Yeah, absolutely.
which is at what point does something become just too clever for its own good?
Because the stakes here, they aren't just about code syntax or, where to put a semicolon. It's fundamentally about cognitive load.
Right.
It's that friction between the mental effort required to read and decipher information versus the mechanical efficiency of writing it in the first place.
Yeah, writing it fast versus reading it easily.
Exactly. And to understand this tension, we really have to look at the incredibly difficult mindset shift required to move from sequential step-by-step logic.
Which is what we naturally do as humans, right?
Right. Totally natural to pure functional abstraction.
Okay, let's unpack this, because I think we have to start by setting up this problem with a little bit of historical context.
I know that's a good idea.
Specifically looking at an older programming language called Perl. Perl. Now, Perl is famous, or maybe infamous is the better word.
Definitely infamous.
Yeah, infamous for this core philosophy known as there's more than one way to do it. Or TMTOTDI, if you want the acronym.
TMTOWTDI, right? And on paper, that sounds incredibly liberating, doesn't it?
It sounds great.
It sounds like creative freedom. I mean, if you're a programmer and you're tired of rigid corporate systems dictating every single keystroke, a language that says, hey, solve this however your brain works, is deeply appealing.
Sure, you get to express yourself.
But historically, this philosophy led to some deeply, deeply obfuscated code.
Because everyone was just doing their own thing.
Exactly. Because everyone can do it their own unique way, Perl developed this incredibly noisy syntax. It was just absolutely full of special characters.
Like symbols everywhere.
Everywhere. It became a language where you could write a highly functional program that essentially looked like, a string of random punctuation marks.
It's an absolute alphabet soup.
Yeah.
And there is a direct parallel between that old Perl philosophy and the modern experience of writing in Haskell. Which, for context, Haskell is a pure functional programming language, and it has its own version of this alphabet soup, where readability is just frequently sacrificed at the altar of brevity.
Right.
It's short, it's elegant, but to an untrained, good luck reading it.
And to really understand why that sacrifice happens, we
Yeah.
have to contrast it with the alternative, which is the imperative style of programming.
Okay, break that down for us.
So imperative programming is what most people naturally think of when they imagine coding. It is explicit, it can be very wordy, sure, but the logic branches are glaringly obvious.
Right.
It's a very straightforward series of commands. Do this, then do that.
Think about it like this for you listening. Imperative programming is like giving someone turn-by-turn driving directions.
So that's a good analogy.
Right. Like take a left on Main Street, drive 2 miles, turn right at the gas station. It takes a long time to say, and you've got to write it all out, but nobody gets lost. The logic is totally explicit. Functional programming, on the other hand, is more like handing someone a teleportation device. It's accurate.
It gets you there instantly. But if you don't intimately know how the internal mechanisms and buttons of that teleporter work, you're going to end up materialized inside a wall.
Yeah, you're just staring at a black box. And the reason that explicit step-by-step logic feels safer to us isn't just about programming.
What is it about, then?
It's about human psychology. Humans naturally process the world in an imperative flow. We operate on a check and act basis.
It can act.
Yeah, like you check if it's raining outside. If it is, you act by grabbing an umbrella.
Right, simple.
And in programming, that maps directly to an if statement or a match case. It mirrors our internal monologue.
So what does functional programming do to that?
Well, what functional elegance does is it strips away that familiar check and act narrative to create something mathematically purer, but it forces us to ask a really vital question.
Which is,
How often do we mistake fewer words for better communication?
wow. Yeah, that brings us perfectly to a very specific, granular example from the notes of how this actually plays out on the screen. Right, let's get into the weeds a bit.
Let's look at a really common scenario. Refactoring an imperative script into a higher order functional approach. There's this well-known exercise in the Haskell community where someone takes a perfectly readable, explicitly written function and they condense it down using pure functional logic.
Hmm.
And the grand prize for this massive mental leap, saving exactly 3 lines of code.
Yeah, just 3 lines.
That seems wild.
And when you look at the raw numbers, saving 3 lines hardly seems worth the effort.
Not at all.
It is really only an improvement if you were already intimately familiar with the inner workings of the language.
Yeah.
To see why, we should look at the specific function used in this kind of refactoring. It's called prelude.maybe.
Okay, so to understand what prelude.maybe does, you first have to understand what it's acting upon,
Right.
which in Haskell is called a maybe context. And a maybe context is basically just a conceptual box.
Box, yeah.
It represents a value that might exist or it might not. You open the box, and there is either a concrete, tangible value inside, or it is simply nothing.
Just empty space.
Right. So the prelude maybe function acts as a helper tool. It takes that uncertain metal, maybe box, and collapses it down into a solid concrete result that the rest of the program can confidently use without crashing.
Exactly. But the mechanism of how it collapses that box is where the density really comes in.
Yeah, the alphabet soup.
Right. The way it's written in this refactored, so-called elegant code relies on a very specific syntax quirk. It's called a section.
A section.
Yeah. And visually, a section looks like an open parenthesis, a colon, the word body,
Oh.
and a closed parenthesis, so body.
Okay, and we really need to explain how that actually operates physically on the data. Because if you just look at that open paren colon body, it looks like a typo to someone who is used to explicit instructions.
It really does.
Yeah.
So a section is a very specialized tool for dealing with binary operators.
In binary operators,
It's simply a symbol that requires 2 arguments to work, a left side and a right side.
like a plus sign.
Exactly like a plus sign. You need a number on the left and a number on the right for plus to actually mean anything.
Right, you can't just say plus.
No.
Mm.
So in Haskell, a colon acts as a binary operator that attaches an item to the front of a list.
Okay.
What a section does is it locks in only one of those 2 required sides.
Oh, weird.
Yeah. It's the equivalent of writing +5 and just leaving it hovering in the air.
Just waiting.
Exactly. It turns an operator into a waiting function. It's locking in half of the equation and leaving the other half completely blank, just waiting for input to fall into it.
Okay, so if you don't use this obscure section syntax, your fallback is writing it out using a lambda function.
Right, the lambda.
And for those of you who might not spend your days reading programming manuals, a lambda is essentially an anonymous throwaway function that you just write on the fly. Instead of leaving a blank space like a section does, a lambda forces you to explicitly spell out the variables. You'd have to write out, take this specific variable x and attach it to this specific body.
Right, you have to name everything.
It is much more explicit, but it completely ruins that 3-line brevity the functional programmer is aiming for.
It adds all that wordiness back in.
Now, I have to push back on this whole concept.
Okay, let's hear it.
Because if you have to master obscure terminology like sections and maybe contexts and anonymous lambda functions, just to save 3 measly lines of code on a screen.
Yeah.
Isn't that a massive step backward for actual real-world productivity?
Well,
I mean, imagine trying to read a novel where every third paragraph is replaced by a single, incredibly dense emoji.
that would be exhausting.
Right. Sure, the book is physically thinner, and maybe the author feels incredibly clever for conveying so much meaning in a tiny picture. But as a reader, you're constantly stopping to look up what the emojis mean.
What's fascinating here is that your frustration mirrors the exact learning curve every developer hits when they encounter this.
Really?
Oh, absolutely.
Uh,
The density feels hostile.
Yeah.
But the density isn't a bug in the system, it's a feature.
A feature.
Well, at least it's a feature for those who are completely fluent in the language.
Mm.
The goal of this density isn't just to save physical space on a hard drive. It forces the programmer to elevate their level of abstraction.
Okay, what do you mean by that?
You are no longer dealing with line-by-line execution. You are dealing with high-level concepts and relationships between data types. The code becomes a mathematical definition of a solution rather than a recipe of steps to get there.
Okay, I hear you, but even knowing that, the actual structure of this dense code feels completely backward to human intuition.
It does.
Let's look at how this prelude.maybe function is actually built from the inside out. It expects exactly 3 arguments to do its job.
Right.
It needs a default value, it needs an action to perform if the box isn't empty, and it needs the maybe box itself. But the very first argument it requires you to provide is the default value.
Which, to an imperative check and act mind, is deeply weird.
It's so weird.
Yeah, you naturally want to check the box first. Like, is there something inside? If no, use the default. If yes, use the item.
Exactly. Why would you establish the default fallback before you even check the value you're looking for?
Right.
It's like going into your phone settings and setting a custom ringtone for a contact before you've even entered their phone number or name into the device.
It's a great way to put it.
You are establishing the environment before the data even arrives. It just feels completely out of order.
But this brings us to the absolute genius of the system. That backward-feeling order is a highly deliberate design choice.
Okay.
It is built this way specifically to favor something called partial application and function composition.
Okay, let's define partial application. Because looking at the notes, this is the real aha moment of the deep dive.
It really is. So partial application is the mechanical approach of giving a function fewer arguments than it actually expects.
Okay.
Normally, if a function needs 3 things and you give it 1, it breaks. But when you do that in a language like Haskell, the function doesn't crash or throw an error.
What does it do?
Instead, it returns a new function that absorbs what you gave it and is now just quietly waiting for the remaining arguments.
Okay, let's ground this in a specific scenario for the listener. Let's say you have a program that needs to constantly print out the names of items inside these maybe boxes. If the maybe box was the first argument required by the function, you'd be forced to write out those incredibly clunky explicit lambda functions we talked about earlier.
Right, you'd have to constantly create placeholder variables just to manage the flow of data coming in.
Exactly. But by putting the default value first, all of that clunkiness just vanishes.
Yeah.
Here's where it gets really interesting. The best way to visualize partial application is to think of a factory assembly line.
Okay, I like this.
By putting the default value first, you are essentially building the entire processing machine on the factory floor and turning the power on.
Right.
That's the partial application. You fed it the default value. You told it what action to perform, so the machine is fully constructed, but it's just sitting there humming, waiting.
Just waiting for the data.
Yes. Then, whenever a maybe box comes traveling down the conveyor belt, the machine instantly processes it. If the order were reversed, if the maybe box had to come first, you couldn't pre-build the machine. You would have to build a brand new custom machine from scratch for every single item that came down the belt.
But if we connect this to the bigger picture, it highlights a profound philosophical shift in how we interact with systems.
How so?
Well, partial application represents a shift from telling a computer what to do step by step to defining what things are.
Oh, wow.
Yeah. When you pre-build that machine on the assembly line, you aren't writing a list of instructions anymore. You are establishing a permanent state of being.
Yeah.
You are saying, this is a machine that handles defaults.
Yeah.
It is an incredibly powerful, elegant way to design a system once you understand the architecture.
Once you understand the architecture, I mean, that is the million-dollar caveat, isn't it?
It really is.
Because the reality of moving away from the mechanics of partial application and dealing directly with the human element is intense. The actual psychological friction of trying to learn and apply this pure functional mindset in daily coding is staggering.
It is not a trivial transition, and it's a known phenomenon in the programming community that prior experience doesn't necessarily save you.
Even if you know other languages.
Yeah, someone can have extensive experience in other functional-leaning programming languages, like Elixir, for example.
Okay.
Elixir is a fantastic language that utilizes functional concepts, but it doesn't strictly enforce mathematical purity the way Haskell does. You can still hold on to a little bit of that sequential step-by-step thinking in Elixir.
You still have a safety net.
Exactly.
But switching to Haskell's pure functional ways requires massive conscious adjustments because it rips away that safety net. It's an acknowledgement that the journey to mastery is incredibly long, and those old imperative check and act habits die incredibly hard.
Oh, they do.
You can spend months studying this. You can write 99 distinct deep dives or 99 separate programs exploring a language like Haskell and still find yourself grappling with the mental friction of partial application.
Yeah, that's true.
You can intellectually understand the factory assembly line, but your hands still want to build the machine from scratch every time.
Because it feels safer.
Right. So what does this all mean for you, the listener, if you aren't a programmer? Why should you care about the order of arguments in a piece of code you'll never write? How does the struggle to learn this alphabet soup apply to learning any highly specialized, abstract skill?
Well, it tells us that true mastery often requires actively unlearning the very things that make us feel competent and comfortable.
Unlearning.
Yeah. We rely on explicit, wordy logic, whether it's imperative code, micromanaging a team at work, or over-explaining a concept in a meeting.
Oh, we all do that.
We do it because it feels safe. We like to see every step of the process. We like to chop the carrots ourselves.
Right?
Stepping into true elegance requires a massive leap of faith. It requires trusting the hidden architecture, like that hidden assembly line of partial application, enough to let go of that step-by-step control.
You just have to let it work.
You have to trust the system to do the work without you holding its hand.
Unlearning what makes us comfortable to achieve elegance.
Yeah.
Let's recap the journey we've taken today. We started in the messy, noisy history of Perl and the chaos of more than one way to do it.
The alphabet soup?
Exactly. We contrasted that with the wordy, step-by-step safety of imperative traditional coding. Then we dove headfirst into the dense, highly abbreviated logic of Haskell. We decoded the mechanics of a maybe function, breaking down specialized tools like sections and lambdas. We uncovered the brilliant assembly line logic of partial application by understanding why the default value comes first.
And we realized that achieving functional elegance requires a deeply painful but ultimately rewarding mindset shift.
Which raises an important question to ponder as we wrap up today.
Lay it on us.
We often assume that the ultimate goal of communication, whether it's writing computer code, drafting legal documents, or just having a daily conversation, is absolute crystalline clarity.
We want to be understood.
Right. We want everyone to understand us perfectly the first time. But if true mastery and ultimate elegance actually look like an incomprehensible alphabet soup to an outsider,
Yeah.
does that mean the highest levels of expertise are inherently isolating?
Oh, wow.
Next time you see something dense, highly optimized, and totally confusing, ask yourself, is this poorly written, or are you just not yet equipped to see the elegance?
If you're staring at the metaphorical black box and all you see is an impenetrable wall, maybe the problem isn't the box. Maybe it's an invitation to elevate your level of abstraction. Thank you so much for joining us on this deep dive. Keep questioning the information around you, and we'll see you next time.